Hi, I am Dilmini Vijayasinghe from Stevens Neuroimaging and Informatics Institute, University of Southern California. Thank you for watching my digital poster for ISMRM 2023. The title of our abstract is Statistical Evaluation of Complexity Tests for fMRI Time Series Data. Complexity is a measure of irregularity of a dynamic system. In resting state fMRI, we can apply this technique to analyze complexity of the time series signal. There are numerous methods to measure complexity in resting state fMRI time series signals. In this study, we used fractal dimension-based complexity methods and entropy-based complexity methods. We obtained resting state fMRI data from the Nathan Klein Institute Rockland sample. It is a random selection of multi-band resting state fMRI scans of 20 subjects, which includes 11 female participants and 9 male participants, age ranging from 15 to 73. All subjects underwent resting state fMRI with 3 different sequences. The complexity was measured using an in-house toolbox called Loft Complexity Toolbox 2.0. The toolbox can perform 7 different complexity tests: Higuchi fractal dimension, Hurst exponent, Lempulsive complexity, approximate entropy, multi-scale sample entropy, fuzzy entropy, and permutation entropy. We chose multiple values for each parameter in a complexity test. The goal of this study is to evaluate the optimal parameter selection in these complexity tests and effect of temporal resolution of resting state fMRI data. 4-dimensional fMRI images were pre-processed using Contoolbox. Pre-processing steps includes motion realignment, regression of motion parameters, regression of CSF white matter signal fluctuations, linear drift removal using high-pass filter, co-registration to individual T1 space, and normalization to MNI space. Next, we created surrogate data by applying random permutations for voxel-wise time series signal of the empirical data. Complexity of time series signals were measured using Loft Complexity Toolbox for each subject scan for all the complexity tests and all the combinations of parameters. The complexity maps are 3-dimensional images. We segmented the complexity maps into CSF and gray matter. Then, mean complexity values were calculated for gray matter and CSF. These steps were repeated for surrogate data and for all the temporal resolutions. For the statistical analysis, we used MATLAB repeated measures ANOVA model followed by post-hoc tests. Complexity results for empirical fMRI time series signal. Each square represents the difference between mean complexity of CSF and gray matter. Complexity should be able to distinguish signals from gray matter and CSF, as gray matter is assumed to show greater complexity. Likewise, in surrogate data, that difference should disappear. So we expect blue squares, which represents the high mean complexity in gray matter. Multi-scale sample entropy shows good discrimination between CSF and gray matter for a wide parameter space and in all 3 fMRI protocols. White asterisk denotes the differences of mean complexity that are statistically significant. Complexity results for surrogate fMRI time series signal. There are no significant differences between mean complexity of gray matter and CSF in temporally randomized time series signals. Overall, MSE, fuzzy entropy, and Hurst exponent showed significantly higher mean complexity of gray matter compared to CSF for all 3 fMRI protocols. For surrogate data, differences between mean complexity values of gray matter and CSF were minimal and did not reveal significant differences for most of the parameter settings. We recommend using multi-scale sample entropy at low-frequency scales since it showed robust discrimination between gray matter and CSF signals. This study was supported by the National Institute of Health. Our acknowledgement also extends to Nathan Klein Institute, Laboratory of Functional MRI Technology at USC Stevens Neuroimaging and Informatics Institute, and USC Laboratory of Neuroimaging. Thank you.